Since the earliest centuries, humans have looked to the stars with awe and curiosity, feelings that were both inspiring and intimidating. The night sky was not just a canvas of twinkling points of light. For ancient civilizations, it was a map of unknown worlds, full of mystery and potential. Every planetary movement, every comet's passage became an object of observation, study, and sometimes myth. However, it was not until the 20th century that dreams of traveling to the stars became tangible reality. Human spaceflight marked one of the most significant milestones in the history of civilization. On April 12, 1961, Yuri Gagarin completed the first orbital flight, spending 108 minutes circling the Earth. This historic achievement demonstrated that humans could exist beyond their home planet, even if only for a limited duration. From that moment onward, new questions arose. How long can humans survive in microgravity conditions? To what extent can the body adapt to the unfamiliar environment? And what threats do radiation and limited resources pose to life in space? Living outside Earth is not merely a journey through space. It is a test of biological, psychological, and social limits. Space imposes stringent demands: extreme temperatures, zero gravity, high levels of radiation, and limited access to food, water, and breathable air. Even short missions reveal significant changes in the human body. The cardiovascular system responds to fluid redistribution, muscles lose tone, bones lose density, and immune function declines. Every new experiment underscores that humans are products of Earth, and that survival beyond the planet requires protective technologies and careful preparation. The history of space exploration is full of examples in which knowledge was gained through experimentation. Early suborbital flights gradually led to orbital missions aboard spacecraft such as Soyuz and Apollo, followed by long-term research aboard space stations like Salyut, Mir, and the International Space Station, ISS. Each human presence in orbit was not only a technological achievement, but also a source of unique data about how the human body functions in an unfamiliar environment. Particular attention is paid to the effects of microgravity and radiation. In weightless conditions, muscles atrophy, bone tissue loses calcium, increasing the risk of osteoporosis. Prolonged exposure to cosmic radiation elevates the risk of cancer and can induce DNA mutations. Even with modern shielding technologies, these factors limit the duration of safe human habitation in space. Beyond biological limitations, space presents profound psychological challenges. Isolation, confinement, and limited social contact create stress, anxiety, and depression. Experience from missions aboard the ISS shows that adaptation requires discipline, mental resilience, and a supportive environment. Each day spent away from Earth tests the human mind as much as the body. Currently, the record for the longest continuous spaceflight is held by Russian cosmonaut Valery Polyakov, who spent 437 days aboard the Mir space station. This record demonstrates the outer limits of human endurance, while also showing that the body can gradually adapt when maintained with proper exercise, diet, and medical monitoring. However, each subsequent mission presents new challenges: how to counteract muscle and bone loss, how to protect against radiation on longer missions, such as those to Mars or beyond, and how to maintain psychological stability over extended periods of isolation. Nutrition and hydration are key aspects of life beyond Earth. In space, astronauts cannot rely on natural food sources. Specialized diets are designed to provide all essential nutrients. Water, a critical resource, must be recycled and purified carefully. Even short-term deficiencies can have profound effects on the human body, making long-duration missions extremely demanding. Social and technological factors are also critical. Astronauts live in tightly confined crews where every action is planned. Team dynamics, task allocation, and adherence to strict schedules of sleep and activity are vital for survival and mission success. Any misstep can have catastrophic consequences, demonstrating that life beyond Earth is not only a physical challenge but a moral and operational one as well. Technology plays an essential role in extending human life in space. Life support systems, protective suits, air and water filtration units, and medical devices allow astronauts to survive in environments that would otherwise be instantly lethal. Modern research indicates that without these technologies, a human would survive only minutes or hours in open space, emphasizing the fragility of life beyond Earth's atmosphere. Thus, life beyond Earth is a constant balance between biological constraints, psychological challenges, and technological capabilities. Every new experiment, every mission to orbit or another planet, expands scientific understanding of human endurance limits. While current missions rarely exceed 1 year in duration, research paves the way for a future where humans may live for years or even decades in space, provided adequate conditions and protections are established. This documentary will continue exploring this topic, delving into the history of space exploration, the effects of microgravity, radiation, psychological challenges, and technologies designed to extend human survival beyond Earth. Each chapter will provide a thorough analysis, drawing from scientific research, experimental studies, and the experiences of astronauts, to answer the question, how long can a human survive in space, and under what conditions is life sustainable beyond Earth? The story of human space exploration is one of ambition, competition, and scientific curiosity. For centuries, humans had gazed at the night sky, tracking celestial movements and constructing intricate calendars and astronomical models. Yet, the dream of leaving Earth remained purely theoretical until the 20th century, when technological advances and geopolitical tensions converged to transform imagination into action. The space age began in earnest with the launch of Sputnik 1 by the Soviet Union on October 4, 1957. This small, spherical satellite, weighing just 83 kilograms, circled the Earth and transmitted radio signals, demonstrating that artificial objects could sustain orbit. The launch of Sputnik shocked the world and ignited a fierce competition between global powers, particularly the United States and the Soviet Union, to dominate space. The Cold War rivalry catalyzed the rapid development of rocket technology, satellite communications, and human spaceflight capabilities. Only 4 years later, in April 1961, Yuri Gagarin became the first human to travel into space aboard Vostok 1. Orbiting the Earth once, he completed a journey that lasted 108 minutes. Gagarin's flight was not merely a symbolic achievement, it was a critical experiment in understanding human tolerance to the stresses of space travel, including acceleration, weightlessness, and isolation. The data collected during his mission laid the groundwork for the physiological and psychological studies that continue to inform modern space exploration. Shortly afterward, the United States accelerated its own efforts with the Mercury program, which tested human spaceflight under increasingly demanding conditions. Alan Shepard became the first American in space in 1961, completing a suborbital flight that lasted just over 15 minutes. Following Mercury, the Gemini program in the mid-1960s introduced longer flights, orbital rendezvous, docking procedures, and extravehicular activity, EVA, or spacewalking. These missions were crucial in demonstrating that humans could survive and perform complex tasks in microgravity, setting the stage for more ambitious projects. The pinnacle of early space exploration was the Apollo program, which aimed not only to reach orbit but to land humans on another celestial body. On July 20, 1969, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin became the first humans to walk on the Moon, while Michael Collins orbited above in the command module. The Apollo missions provided an unprecedented wealth of data about human adaptation to extreme environments, including exposure to radiation, lunar gravity, and prolonged confinement. They also demonstrated the importance of technological innovation in enabling life support, navigation, and communication beyond Earth. During the 1970s and 1980s, the focus shifted from short-term missions to sustained habitation of space through space stations. The Soviet Salyut program introduced a series of orbital laboratories, allowing cosmonauts to conduct long-duration experiments in microgravity. These missions revealed the profound physiological effects of extended weightlessness, including muscle atrophy, bone density loss, and cardiovascular deconditioning. At the same time, astronauts faced challenges in maintaining psychological stability, as confinement and isolation intensified stress and anxiety. Lessons learned from Salyut laid the groundwork for future long-term habitation strategies. In 1986, the Soviet Union launched Mir, the first modular space station, which allowed for progressively longer human stays in orbit. Crews aboard Mir conducted medical, biological, and technological experiments that advanced understanding of human endurance in space. Data collected on Mir demonstrated that humans could live and work in orbit for over a year, though not without physiological and psychological challenges. Muscle degeneration, bone loss, vision changes, and shifts in circadian rhythms were all documented, providing critical insights into the limits of human adaptation. The establishment of the International Space Station, ISS, in 1998 marked a new era of global cooperation and long-duration habitation. The ISS functions as a multinational laboratory orbiting Earth, where astronauts and cosmonauts from different countries conduct experiments in biology, physics, medicine, and engineering. Current missions last 6 months or longer, with some extending up to a year, and studies continue to reveal both the vulnerabilities and resilience of the human body in space. Every crew member contributes to a growing database on nutrition, exercise, and life support that informs future missions to the Moon, Mars, and beyond. Historical missions also underscore the challenges and risks inherent in space exploration. Accidents such as the Apollo 1 fire, the Space Shuttle Challenger disaster, and the Columbia tragedy remind us that space is unforgiving. These events accelerated safety protocols and technological improvements, emphasizing redundancy, monitoring, and robust training. They also highlight the fact that survival in space is contingent not only upon human physiology but upon flawless engineering and preparation. As exploration expanded, private companies began entering the space industry, adding a commercial dimension to the history of spaceflight. Companies like SpaceX, Blue Origin, and Virgin Galactic are developing reusable launch vehicles, commercial orbital stations, and even plans for interplanetary travel. This democratization of space introduces new opportunities for long-term human presence beyond Earth, though it also underscores the persistent limits imposed by human biology and environmental hazards. Today, historical records show that the maximum duration a human has spent in space continuously is 437 days, held by Russian cosmonaut Valery Polyakov aboard Mir. This record illustrates the upper threshold of human endurance in a controlled orbital environment and informs future plans for extended missions, including potential trips to Mars that could last 2 to 3 years. While past missions relied on intensive preparation, careful monitoring, and sophisticated life support systems, future exploration will demand even more advanced solutions to sustain human life in increasingly hostile extraterrestrial environments. The history of space exploration is, therefore, both a record of achievement and a chronicle of human vulnerability. It demonstrates humanity's capacity to transcend earthly boundaries, while simultaneously revealing the physical, psychological, and technological constraints that define our survival in space. By examining the past, we gain critical insights into the challenges that lie ahead for long-term habitation on other planets and the ongoing quest to extend human life beyond Earth. This chapter sets the stage for deeper examination of the physiological and environmental challenges faced by humans in space, which will be explored in the next chapters, including the effects of microgravity, radiation exposure, and prolonged isolation. Understanding this history is essential to predicting how long humans can survive beyond Earth and what technologies will be necessary to ensure their continued existence in the cosmos. One of the most profound challenges of living in space is the absence of gravity, as humans experience it on Earth. Microgravity, an environment in which the force of gravity is greatly reduced, affects nearly every system of the human body. Although astronauts adapt to this condition, the physiological consequences are significant and represent a central concern for long-duration missions beyond Earth. The musculoskeletal system is particularly vulnerable in microgravity. On Earth, muscles and bones are constantly under stress from gravity, which maintains their strength and density. In the weightless environment of space, this mechanical load is removed, leading to rapid muscle atrophy and bone demineralization. Studies conducted aboard space stations such as Mir and the International Space Station, ISS, have shown that astronauts can lose up to 20% of muscle mass and 10 to 15% of bone density during missions lasting 6 months or more. Weight-bearing bones, particularly in the spine, pelvis, and lower limbs, are most affected, increasing the risk of fractures and long-term osteoporosis upon return to Earth. Cardiovascular adaptations to microgravity also pose risks. On Earth, gravity helps regulate blood distribution, pulling fluids toward the lower extremities. In space, fluids shift toward the upper body, causing facial puffiness, nasal congestion, and a condition known as bird legs, in which the legs appear thinner due to fluid redistribution. This shift can reduce plasma volume and impair the heart's efficiency, potentially leading to orthostatic intolerance, difficulty standing upright, once back on Earth. The heart itself may atrophy slightly due to decreased workload, though regular exercise and cardiovascular training can mitigate some of these effects. Microgravity also affects the vestibular system, which controls balance and spatial orientation. Astronauts often experience space adaptation syndrome, a type of motion sickness that results from conflicting signals between the inner ear, eyes, and body. Symptoms include dizziness, nausea, and disorientation. While most astronauts adapt within a few days, prolonged missions can exacerbate these effects, and readjustment upon return to Earth can take weeks. The musculoskeletal and cardiovascular consequences of microgravity are compounded by metabolic changes. Studies indicate that astronauts experience alterations in protein metabolism, calcium homeostasis, and bone remodeling. Loss of calcium from bones can increase the risk of kidney stones, while changes in muscle protein turnover affect strength and endurance. Hormonal changes, including fluctuations in cortisol and other stress-related hormones, further influence the body's ability to maintain homeostasis. Immune function is another critical aspect affected by microgravity. Research on ISS missions has shown that astronauts often experience a reduction in immune cell activity, making them more susceptible to infections. Latent viruses, such as the Epstein-Barr virus, may reactivate during long-duration spaceflight. Combined with the stress of isolation and altered sleep patterns, these immune changes represent a serious concern for human survival on extended missions. Sleep disruption is a common consequence of living in microgravity. The absence of a natural day-night cycle in orbit, combined with continuous artificial lighting and operational demands, leads to irregular sleep patterns. Sleep deprivation affects cognitive performance, mood, and physiological regulation, compounding other health risks. Crew members must adhere to strict schedules and sometimes rely on pharmaceutical aids to maintain alertness and performance. Neurological effects also emerge in long-duration spaceflight. Recent research suggests that microgravity may cause subtle shifts in brain structure and function, particularly in regions controlling balance, vision, and coordination. Intracranial pressure appears to increase slightly in some astronauts, contributing to vision changes known as spaceflight-associated neuroocular syndrome, SANS. These changes can persist for months after returning to Earth, raising concerns for extended missions to Mars and other destinations. Exercise is the primary countermeasure against the deleterious effects of microgravity. Treadmills, resistance machines, and cycloergometers are standard aboard the ISS, designed to mimic gravitational load and maintain muscle and bone integrity. Yet even with rigorous exercise, the body does not fully replicate the conditions experienced on Earth. Nutrition also plays a key role, with diets high in protein, vitamin D, and calcium essential for mitigating bone loss and maintaining muscle mass. Psychological adaptation to microgravity is closely linked to physical changes. The feeling of weightlessness affects movement, perception, and coordination. Simple tasks such as eating, sleeping, or handling tools require adaptation and sometimes creative problem-solving. The mental strain of constantly adjusting to a non-Earth environment can contribute to fatigue, stress, and decreased operational efficiency. The long-term effects of microgravity remain a subject of active research. Data from missions exceeding a year, such as Valery Polyakov's 437-day stay on Mir, show that some effects, like muscle and bone loss, partially reverse after return to Earth, while others, including vision changes and shifts in vestibular function, may persist longer. Understanding these adaptations is critical for planning interplanetary travel, where microgravity exposure could last multiple years. Furthermore, microgravity interacts with other hazards of space, such as radiation and isolation. Reduced gravity can exacerbate the effects of radiation by altering tissue repair processes and immune function. Combined, these factors define the boundary conditions of human life in space and highlight the complexity of sustaining human health beyond Earth. In summary, microgravity fundamentally transforms the human body, affecting muscles, bones, the cardiovascular system, the immune system, neurological function, and psychological well-being. Countermeasures such as exercise, nutrition, and careful mission planning mitigate some risks, but they cannot fully replicate Earth's environment. Microgravity remains one of the central biological challenges to long-duration human spaceflight, defining the limits of survival and the strategies necessary to extend human life beyond our planet. The next chapter will examine the additional threat of cosmic radiation, which, combined with microgravity, presents some of the most significant barriers to long-term human habitation in space. Understanding these threats and developing technological and medical countermeasures is essential to realizing humanity's goal of living beyond Earth. Beyond the physical challenges of microgravity, one of the most formidable threats to human life in space is cosmic radiation. Unlike Earth, where the magnetic field and atmosphere provide substantial protection from high-energy particles, space exposes humans to ionizing radiation originating from the Sun, distant stars, and galactic cosmic rays. Prolonged exposure to this radiation can damage cells, tissues, and DNA, posing significant risks to both short and long-term health. Radiation in space exists in several forms. Solar particle events, SPs, are bursts of energetic protons released by the Sun during solar flares and coronal mass ejections. These events can deliver massive doses of radiation in a short period, potentially causing acute radiation sickness if astronauts are unprotected. Galactic cosmic rays, GCRs, originating outside the solar system, consist of highly energetic nuclei that penetrate shielding materials, depositing energy deep within biological tissues. Unlike SPs, GCRs provide continuous low-level exposure, which accumulates over time and contributes to long-term health risks such as cancer, cardiovascular disease, and neurological damage. On Earth, humans are largely protected from cosmic radiation by the planet's magnetosphere and atmosphere. At sea level, exposure is minimal, roughly 2 to 3 millisieverts per year. But in low Earth orbit, LEO, where the International Space Station orbits, astronauts are exposed to doses up to 150 to 200 millisieverts during a 6-month mission. On interplanetary missions, such as those to Mars, cumulative exposure could reach several sieverts, levels that significantly increase the probability of cancer and other radiation-induced illnesses. For perspective, a single sievert is associated with a 5 to 6% increased risk of fatal cancer, illustrating the severity of prolonged space travel. The biological effects of radiation depend on both the dose and the type of particles involved. High-energy particles can penetrate cell walls and interact with DNA, causing strand breaks, mutations, or chromosomal aberrations. While the human body has DNA repair mechanisms, these processes are not perfect. Accumulated damage can lead to uncontrolled cell growth, resulting in cancer, or cause tissue degeneration, affecting organs such as the heart, lungs, and brain. Additionally, radiation can accelerate aging processes and compromise immune function, exacerbating vulnerability to infections. Radiation exposure is also a critical concern for the central nervous system, CNS. Studies using animal models suggest that high doses of cosmic radiation may impair cognitive functions, memory, and motor skills. Even low-dose, long-duration exposure has been linked to subtle neurological deficits, including changes in brain structure and reduced neurogenesis. These effects raise concerns about the safety of extended missions, where cognitive performance is essential for problem-solving, navigation, and emergency response. Astronauts' skin and eyes are particularly sensitive to radiation. Cataracts are a documented consequence of long-term exposure in space, with some astronauts developing clouding of the lens after multiple missions. Skin damage, including increased susceptibility to sunburn and delayed wound healing, also occurs due to ionizing radiation. While Earth-bound humans rarely experience such effects at ambient radiation levels, the heightened exposure in space presents a clear and present danger. Radiation interacts with microgravity in ways that may amplify its harmful effects. For example, bone loss and microgravity releases calcium into the bloodstream, which may interact with radiation-induced oxidative stress, compounding damage to cardiovascular and nervous tissues. Similarly, weakened immune function due to weightlessness can make the body less capable of repairing radiation-induced DNA damage. These combined factors underscore the necessity of integrated countermeasures for long-duration spaceflight. Protecting humans from space radiation requires both technological and biological strategies. Spacecraft shielding is the primary line of defense. Materials such as aluminum, polyethylene, and advanced composites can absorb or deflect high-energy particles. However, shielding against GCRs remains challenging because the most energetic cosmic rays penetrate even dense materials, creating secondary radiation that can be equally harmful. Spacecraft design, layout, and specialized storm shelters are essential for protecting astronauts during solar particle events. Medical countermeasures are also under investigation. Antioxidants, radioprotective drugs, and gene therapy techniques aim to enhance the body's natural DNA repair mechanisms and reduce oxidative stress. While promising in experimental models, these approaches are not yet fully validated for long-duration human missions, and their effectiveness under continuous cosmic radiation remains uncertain. Historical data from space missions provide insight into radiation risks. Apollo astronauts who traveled beyond low Earth orbit experienced higher radiation doses, though missions were short enough to avoid significant acute effects. Studies of long-term ISS crews, combined with epidemiological data from Earth-based radiation exposure, inform risk models for future interplanetary travel. Current research emphasizes that extended journeys to Mars or other deep space destinations will require unprecedented levels of protection, monitoring, and medical preparedness. In addition to physical and medical threats, radiation presents operational challenges. Continuous exposure can degrade spacecraft electronics and communication systems, impacting mission reliability. Radiation-induced faults may require redundancy, shielding, and repair protocols, adding complexity to mission planning and increasing the importance of astronaut training and resilience. The combination of microgravity and radiation exposure defines the outer limits of human tolerance in space. While humans can survive for extended periods in low Earth orbit, interplanetary missions will push these boundaries to their extreme. Without robust protection and mitigation strategies, the cumulative effects of radiation could reduce mission safety, compromise cognitive and physical performance, and ultimately threaten the survival of crew members. In conclusion, cosmic radiation is one of the most significant barriers to long-term human habitation beyond Earth. Understanding its mechanisms, quantifying risks, and developing effective countermeasures are essential for extending human life in space. As humanity prepares for journeys to Mars, lunar bases, and eventual exploration of deep space, radiation protection will remain at the forefront of research and technological innovation. The next chapter will explore the challenges of nutrition, hydration, and life support in space, which are equally critical to sustaining human life beyond Earth's protective envelope. These factors, in combination with microgravity and radiation, determine the practical limits of survival in the cosmos. Life beyond Earth is not sustained by technology alone. While spacecraft provide oxygen, temperature control, and radiation shielding, nutrition and hydration form the foundation of human survival in space. Food and water are not merely sources of energy. They influence every physiological system, from muscle and bone integrity to immune function and cognitive performance. Ensuring adequate intake and maintaining balance is one of the most complex challenges in long-duration missions. In space, conventional methods of food preparation and storage are impractical. Microgravity prevents liquids and small particles from settling, making pouring, cutting, and cooking difficult. Early astronauts relied on specially packaged meals, freeze-dried, dehydrated, or vacuum-sealed, to prevent spoilage and minimize debris. The Mercury, Gemini, and Apollo programs demonstrated the feasibility of such systems, but they revealed limitations. Meals were often unpalatable, lacked variety, and could fail to provide all necessary nutrients for extended missions. Modern space agencies have refined these approaches. On the International Space Station, ISS, astronauts consume a carefully calibrated diet designed to meet the unique demands of microgravity. Meals are engineered to supply adequate calories, essential macronutrients, vitamins, and minerals. Protein, calcium, and vitamin D are emphasized to counteract muscle atrophy and bone demineralization. Omega-3 fatty acids and antioxidants are included to reduce inflammation and oxidative stress associated with radiation exposure. Despite these innovations, challenges remain. Caloric intake in microgravity must balance energy expenditure with weight maintenance. Astronauts often experience reduced appetite due to fluid shifts affecting the digestive system and altered taste perception in space. The lack of gravity redistributes fluids toward the head, producing facial puffiness and diminished olfactory sensitivity, which can make food seem bland. Over time, inadequate caloric intake may exacerbate muscle and bone loss, impair immune function, and reduce cognitive performance. Mission planners must therefore provide both nutritionally dense foods and strategies to encourage consistent consumption. Hydration presents another critical concern. Water is heavy, limited, and must be recycled efficiently. The ISS employs sophisticated filtration systems to reclaim water from urine, sweat, and condensation. Even minor disruptions in these systems can threaten crew health. Dehydration can lead to cardiovascular strain, kidney stones, and decreased cognitive function. Maintaining electrolyte balance is equally important, as microgravity alters fluid distribution and can disrupt sodium and potassium levels. Food safety is paramount. Microbial contamination in a closed environment can have severe consequences, as there are no immediate medical facilities or fresh supplies. Strict sterilization, packaging, and storage protocols are essential to prevent bacterial or fungal growth. Similarly, food degradation due to prolonged storage or exposure to radiation can reduce nutrient content, posing risks for missions lasting months or years. The psychological role of food should not be underestimated. Meals provide comfort, social interaction, and a sense of normalcy. The monotony of packaged or rehydrated foods can lead to decreased morale and mental fatigue. Agencies like NASA and ESA have explored the inclusion of fresh foods, such as small-scale hydroponic gardens, to improve variety, nutrition, and crew well-being. Growing food in orbit also provides insights into long-term sustainability for interplanetary travel. Special considerations arise for interplanetary missions. On a journey to Mars, resupply is impossible, and food must remain stable for years. Shelf life, nutritional completeness, and packaging efficiency become critical constraints. Innovations such as 3D printed meals, cultured meat, and algae-based proteins are being investigated to provide diverse, sustainable nutrition. Each solution must balance practicality, taste, and physiological requirements under space conditions. Supplements play an essential role in supporting astronaut health. Vitamin D supplementation is crucial due to the absence of sunlight exposure, which would otherwise allow natural synthesis in the skin. Antioxidants, minerals, and amino acids are tailored to mitigate the effects of radiation, bone loss, and muscle atrophy. Monitoring intake ensures that deficiencies or imbalances do not compromise mission success or long-term health. Hydration and nutrition are intimately linked to other physiological challenges. Adequate water intake supports cardiovascular function and thermoregulation, while proper nutrition bolsters immune defenses compromised by microgravity and radiation. The interaction between diet, exercise, and life support systems illustrates the interdependence of human biology and technology in sustaining life in space. Research on nutrition in space has revealed unexpected effects. For instance, iron metabolism changes in microgravity, potentially affecting red blood cell production. Sodium retention patterns differ from Earth-based norms, impacting fluid balance and cardiovascular function. Digestive processes slow down, altering nutrient absorption and requiring careful monitoring of gastrointestinal health. Understanding these subtleties is essential for preventing long-term complications and ensuring crew performance. Psychological strategies complement physical nutrition. Encouraging meal routines, providing variety in taste and texture, and allowing some autonomy in food selection contribute to well-being. The social aspect of shared meals fosters cohesion, reduces stress, and reinforces a sense of purpose. These elements are as critical as the nutritional content itself, particularly on missions lasting many months or years. In conclusion, sustaining human life in space requires a holistic approach to nutrition and hydration. Microgravity, limited resources, and psychological factors create complex challenges that demand careful planning, monitoring, and innovation. As humanity contemplates long-duration missions to the Moon, Mars, and beyond, advances in food science, water recycling, and dietary optimization will determine the boundaries of human survival. Without proper nutrition and hydration, even the most technologically advanced spacecraft cannot support life. The next chapter will explore the psychological challenges of long-duration space missions, highlighting how isolation, confinement, and extreme environments shape human behavior, resilience, and the limits of endurance in space. While the human body faces profound physical challenges in space, the mind contends with equally formidable pressures. Extended missions beyond Earth place astronauts in environments that are isolated, confined, and far removed from the familiar structures of daily life. These conditions introduce a complex array of psychological stressors that can affect mental health, cognitive performance, and mission success. Understanding and mitigating these challenges is essential for sustaining human life on long-duration space missions. Isolation is among the most significant psychological stressors in space. Astronauts on the International Space Station, ISS, experience prolonged separation from family, friends, and society. Communication delays with Earth, especially for interplanetary missions, amplify feelings of loneliness and distance. For a mission to Mars, the delay can exceed 20 minutes one way, making real-time interaction impossible. This separation increases stress and may lead to anxiety, depression, or a sense of disconnection from reality. Confined living quarters exacerbate stress. Spacecraft and stations offer limited personal space, often only a few cubic meters per individual. Privacy is minimal, and noise from life support systems, machinery, and crew activity is constant. Over time, this confinement can generate irritability, fatigue, and interpersonal tension. Crew members must learn to coexist in close quarters, managing conflicts, respecting personal boundaries, and maintaining team cohesion under pressure. Monotony and sensory deprivation pose additional risks. The lack of natural light, changes in scenery, and repetitive routines can lead to cognitive dulling and mood disturbances. Astronauts may experience decreased motivation, attention lapses, and difficulty concentrating on complex tasks. To counteract these effects, missions incorporate structured schedules, recreational activities, virtual reality experiences, and opportunities for personal hobbies. Maintaining mental stimulation is essential to prevent cognitive decline and preserve psychological resilience. The stress of high-stakes responsibility further impacts mental health. Astronauts are responsible not only for their own safety but for that of their entire crew. Errors can have immediate and catastrophic consequences. The constant vigilance required in monitoring spacecraft systems, conducting experiments, and performing extravehicular activities creates a sustained level of stress that, without mitigation, can lead to burnout, anxiety disorders, or impaired decision-making. Sleep disruption is a common psychological and physiological challenge in space. The absence of a natural day-night cycle, combined with operational demands, results in irregular sleep patterns. Artificial lighting, equipment noise, and microgravity itself alter circadian rhythms. Sleep deprivation affects mood, cognitive performance, and reaction times, compounding the psychological strain of long-duration missions. Strict schedules, controlled lighting, and in some cases, pharmacological aids are employed to maintain adequate rest. Cultural and interpersonal factors play a significant role in psychological well-being. International crews on the ISS include individuals from diverse backgrounds, languages, and professional cultures. While diversity enriches collaboration, it also introduces potential for misunderstandings, conflicts, and communication challenges. Crew selection, training, and team-building exercises aim to mitigate these risks by fostering mutual respect, empathy, and effective conflict resolution. Stress from prolonged spaceflight can also manifest physically, creating a psychosomatic feedback loop. Anxiety and depression can influence appetite, cardiovascular function, immune response, and sleep quality, which in turn affect mood and cognitive performance. Effective coping strategies, including mindfulness, exercise, structured routines, and access to psychological support, are crucial for maintaining equilibrium. Historical missions provide valuable insights into these challenges. During Skylab, Mir, and ISS expeditions, astronauts reported feelings of isolation, frustration with confined environments, and anxiety related to prolonged absence from Earth. Long-duration missions, such as Valery Polyakov's 437-day stay on Mir, revealed that mental resilience is as important as physical fitness in sustaining health and performance. Observations indicate that well-prepared crews with strong interpersonal dynamics and psychological support maintain higher operational efficiency and lower levels of stress. Advanced space missions, including interplanetary travel, amplify these psychological challenges. For example, a trip to Mars could last 2 to 3 years, with months of isolation from Earth and limited external stimulation. This prolonged confinement demands exceptional psychological preparation, adaptive coping strategies, and onboard support systems. Virtual reality environments, telepresence with family and experts, and carefully designed recreational activities are among the strategies being developed to mitigate the mental strain of such missions. Training programs for astronauts now emphasize psychological resilience. Crew members undergo simulation exercises that mimic isolation, confinement, and operational stress, preparing them for the challenges of deep space missions. Selection processes prioritize individuals with emotional stability, adaptability, and strong interpersonal skills. Ongoing mental health monitoring, combined with proactive interventions, ensures that psychological stress does not compromise mission safety or individual well-being. Another critical factor is the perception of risk and uncertainty. Spaceflight involves inherent dangers, including equipment failure, medical emergencies, and environmental hazards. The awareness of these risks can heighten anxiety, particularly on missions with no immediate possibility of rescue. Strategies to address this include intensive training, redundancy in systems, clear operational protocols, and psychological support designed to enhance confidence and coping ability. In conclusion, the psychological challenges of long-duration spaceflight are multifaceted, encompassing isolation, confinement, monotony, operational stress, sleep disruption, and interpersonal dynamics. These factors interact with physiological stressors to shape overall human resilience in space. Successful long-duration missions require an integrated approach that combines careful crew selection, psychological training, structured schedules, social support, and opportunities for recreation and mental stimulation. Understanding these challenges is essential for planning future missions beyond Earth orbit, including voyages to Mars and potential permanent settlements on other planets. The human mind, like the body, has limits that must be respected and supported. By addressing psychological factors alongside physical and technological considerations, space agencies can extend human life in space, ensuring that astronauts remain healthy, functional, and capable of performing the critical tasks required for survival in the cosmos. The next chapter will examine biological experiments and models used to study human adaptation to space, including how these insights inform strategies for long-term survival beyond Earth. Understanding human survival in space requires more than observing astronauts on missions. It demands systematic research using biological experiments and human models to study the effects of microgravity, radiation, isolation, and other hazards. These experiments provide crucial insights into how the human body adapts to the space environment and inform strategies to extend human life beyond Earth. From the earliest days of space exploration, scientists recognized the importance of studying living organisms in orbit. Before sending humans, a variety of animals, including dogs, monkeys, and mice, were launched aboard rockets to observe physiological responses to weightlessness and acceleration. The Soviet Laika missions in the 1950s, despite their tragic outcomes, demonstrated that mammals could survive brief periods of spaceflight. Similar experiments by the United States, including primate flights, allowed researchers to monitor cardiovascular, neurological, and muscular responses to microgravity, providing the foundation for human adaptation studies. The introduction of long-duration space stations enabled more sophisticated biological research. On Salyut and Mir, astronauts conducted experiments with both humans and model organisms. Rodents, insects, amphibians, and plants were studied to understand muscle atrophy, bone demineralization, cellular metabolism, and developmental biology in microgravity. These studies revealed fundamental physiological changes, such as decreased calcium deposition in bones, alterations in cell signaling pathways, and modifications in immune response. Observing these changes in animal models allowed scientists to predict similar effects in humans and develop countermeasures. Human experiments have also been integral to understanding the mechanisms of adaptation. Detailed monitoring aboard the International Space Station, ISS, includes daily measurements of heart rate, blood pressure, muscle strength, bone density, and hormone levels. Cognitive and psychological assessments complement physiological monitoring, providing a comprehensive picture of human function in space. These experiments not only quantify the impacts of microgravity but also test interventions, such as exercise regimens, dietary supplements, and artificial gravity devices, to mitigate adverse effects. A notable aspect of biological research in space is the study of cellular and molecular responses. Microgravity and radiation influence gene expression, protein synthesis, and DNA repair mechanisms. Experiments using human cell cultures have shown that space conditions can alter cell proliferation, induce oxidative stress, and trigger DNA damage. These findings highlight the vulnerability of human tissues to the space environment and underscore the importance of protective measures, including pharmacological interventions and shielding technologies. Animal models have revealed unexpected insights. For example, studies of mice aboard the ISS demonstrated that microgravity affects neurological function, including changes in motor coordination, spatial memory, and vestibular adaptation. Plant studies have shown that growth patterns, root orientation, and cellular differentiation are altered in low gravity, offering clues about how life adapts to non-Earth environments. These insights are critical for planning long-term missions, where sustainable food production and environmental management will be essential. Simulated environments on Earth also provide valuable information. Bed rest studies, where volunteers lie with their heads slightly tilted downward for weeks or months, mimic aspects of microgravity, such as fluid shifts and muscle unloading. These experiments allow researchers to test countermeasures, monitor cardiovascular changes, and investigate bone loss in controlled settings. Combined with in-flight research, Earth-based simulations enhance understanding of human physiology and inform mission planning. Artificial gravity experiments have explored potential solutions to the challenges posed by microgravity. Centrifuge-based studies, both on Earth and in orbit, examine whether rotational force can prevent muscle atrophy, maintain bone density, and support cardiovascular function. While large-scale artificial gravity for long-duration missions remains technologically complex, these studies demonstrate that creating gravitational load may be key to sustaining human health on interplanetary journeys. Nutrition studies and biological models complement human experiments. Rodents and primates in orbit have been fed diets supplemented with calcium, vitamin D, antioxidants, and other nutrients to mitigate bone loss and oxidative damage. These experiments provide critical data for designing astronaut diets that address the specific metabolic and physiological challenges of spaceflight. The interaction between microgravity, radiation, and psychological stress is another focus of study. Experiments combining stress paradigms with exposure to low-dose radiation or simulated microgravity reveal how multiple stressors interact to influence immune function, cognitive performance, and cellular integrity. This integrated approach is essential for predicting outcomes on long-duration missions, where multiple hazards act simultaneously. Technological innovations have expanded the scope of biological research. Miniaturized laboratories on the ISS, automated imaging systems, and remote monitoring tools allow continuous observation of experiments with minimal human intervention. Advances in genomics, proteomics, and metabolomics provide detailed insights into cellular responses, enabling scientists to detect early indicators of physiological decline and to test targeted interventions. Longitudinal studies are particularly valuable. Continuous observation of astronauts and model organisms over months or years allows researchers to track cumulative effects and recovery patterns. Data from these studies help define safe exposure limits, optimize exercise and dietary protocols, and design life support systems capable of sustaining human health on extended missions to Mars or beyond. In conclusion, biological experiments and human models are indispensable for understanding human survival in space. From animal studies to cellular research and simulated Earth environments, these investigations provide the knowledge necessary to predict physiological and psychological responses to prolonged spaceflight. Insights gained guide the development of countermeasures, protective technologies, and operational strategies essential for ensuring the health and performance of humans living beyond Earth. The next chapter will examine technological innovations in life support and habitat design, which are critical for enabling humans to survive and thrive on long-duration missions in space. Sustaining human life in space requires more than understanding physiology and psychology. It demands advanced technology capable of recreating the essential conditions of Earth within the confined and hostile environment of a spacecraft or space habitat. Life support systems and habitat design are central to human survival, providing breathable air, potable water, temperature regulation, waste management, and protection from the hazards of space. Innovations in these areas define the boundary between life and death in orbit and are critical for future long-duration missions beyond Earth. Air supply is the most fundamental requirement for life. In the closed environment of a spacecraft, oxygen must be continuously replenished, and carbon dioxide removed to prevent toxicity. Early spacecraft relied on compressed oxygen tanks, but long-duration missions required more sophisticated solutions. The International Space Station, ISS, employs multiple systems for atmospheric control, including chemical scrubbers that remove carbon dioxide, oxygen generation systems that electrolyze water, and trace contaminant control systems that filter harmful gases. Redundancy is crucial, as any failure in air supply could have catastrophic consequences. Water management is equally vital. Spacecraft cannot rely on resupply from Earth for extended missions, so water must be recycled and purified continuously. Modern systems on the ISS recover water from urine, sweat, and cabin condensation, filtering and sterilizing it to meet potable standards. These closed-loop systems not only conserve resources but also minimize launch mass, a critical consideration for long-duration missions. Advances in filtration materials, microbial control, and automated monitoring have improved the reliability of water recycling, making sustainable life support feasible for months at a time. Temperature and humidity regulation are also essential. Space presents extreme thermal environments, with sunlight creating intense heat and shaded areas plunging to near absolute zero. Habitats must maintain a stable internal climate to ensure human comfort and equipment functionality. Thermal control systems employ radiators, insulation, and heat exchangers to manage temperature fluctuations, while humidity control prevents condensation that could damage electronics or promote microbial growth. Maintaining this delicate balance is essential for both health and operational efficiency. Waste management poses a unique challenge in microgravity. Human waste, including urine, feces, and solid debris, cannot simply be discarded as on Earth. Advanced systems collect, store, and sometimes recycle waste products. For example, urine is purified and reintegrated into the water supply, while solid waste is compressed and stored for eventual disposal. Efficient waste management reduces contamination risks, maintains hygiene, and supports closed-loop life support strategies necessary for long-duration missions. Food preparation and storage technologies complement nutrition research. Freeze-drying, vacuum sealing, and thermostabilization ensure that meals remain safe and nutritionally complete over extended periods. On the ISS, astronauts rely on rehydration packets and prepackaged meals designed for ease of use in microgravity. Research into hydroponic and aeroponic systems enables astronauts to grow fresh produce in orbit, providing not only nutrition but also psychological benefits. Such systems are essential for missions lasting years, where resupply from Earth is impossible. Radiation shielding is a critical aspect of habitat design. While microgravity imposes physiological challenges, cosmic and solar radiation presents a lethal threat. Spacecraft employ layers of aluminum, polyethylene, and advanced composites to absorb or deflect high-energy particles. For long-duration missions, dedicated storm shelters are incorporated into habitat designs, allowing crew members to take refuge during solar particle events. Research continues into innovative materials, including hydrogen-rich polymers and water-based shielding, which provide additional protection without excessive weight. The design of living spaces addresses both functionality and human psychology. Confined habitats must provide adequate personal space, communal areas, and workstations, balancing efficiency with mental well-being. Modular layouts allow for flexibility, enabling the reconfiguration of spaces for different tasks or social needs. Lighting systems mimic Earth's day-night cycle to support circadian rhythms, while visual and auditory elements reduce the effects of monotony and sensory deprivation. Habitat design integrates ergonomics, operational efficiency, and psychological support to sustain human life over months or years. Automation and monitoring technologies are integral to life support. Sensors continuously track air composition, humidity, water quality, and equipment performance. Automated alerts and backup systems ensure rapid response to anomalies, minimizing human error. Advanced control software manages resource allocation, predicts maintenance needs, and integrates environmental data with mission operations. Such systems are critical for deep space missions, where immediate support from Earth may be unavailable. Artificial gravity is another area of technological innovation. Although not yet implemented on a large scale, centrifuge-based habitats or rotating modules are being studied to mitigate the effects of microgravity on muscle, bone, and cardiovascular systems. Research demonstrates that even partial gravity can reduce bone loss and muscle atrophy, offering potential solutions for long-term interplanetary travel. Integrating artificial gravity with existing life support systems remains a complex engineering challenge, but represents a promising avenue for sustaining human health in space. Energy supply and storage are foundational to life support. Habitats rely on solar arrays, batteries, and backup systems to power air circulation, water recycling, temperature control, lighting, and scientific equipment. Redundant power systems ensure continuous operation, while energy-efficient technologies reduce the mass and complexity of life support systems. For missions to Mars or lunar bases, energy independence becomes even more critical, requiring innovations in solar efficiency, energy storage, and distribution. The integration of all these systems defines the success of human habitation in space. Life support technologies, habitat design, and operational protocols must work in harmony to create a sustainable environment. Failures in any subsystem, air, water, temperature, waste, nutrition, or radiation protection, can have cascading effects, highlighting the interdependence of technology, human physiology, and operational planning. In conclusion, technological innovations in life support and habitat design are the backbone of human survival in space. From air and water recycling to radiation shielding, temperature control, waste management, and psychological support, these systems replicate the essential conditions of Earth within the harsh environment of orbit or interplanetary space. Advances in modular design, automation, artificial gravity, and sustainable resource management extend the duration and safety of missions, bringing humanity closer to living beyond Earth. The next chapter will examine the physiological limits and long-term health risks of prolonged space missions, integrating insights from microgravity, radiation, nutrition, and psychological research to define the boundaries of human survival in space. Human survival in space is defined not only by technological capabilities, but by the biological limits of the human body. Microgravity, radiation, isolation, and environmental stressors collectively impose constraints on how long humans can live and function beyond Earth. Understanding these limits is essential for planning long-duration missions, from extended stays in orbit to interplanetary travel. One of the most significant physiological challenges is musculoskeletal degeneration. In microgravity, muscles no longer bear the weight of the body, leading to atrophy. Long-duration missions reveal that astronauts can lose up to 20% of skeletal muscle mass over 6 months, particularly in the lower body and postural muscles. Bone density declines simultaneously, at rates of 1 to 2% per month in weight-bearing bones such as the femur and spine. These changes increase the risk of fractures, kidney stones, and long-term skeletal disorders upon return to Earth. Despite rigorous exercise regimens, complete prevention of muscle and bone loss remains elusive. Cardiovascular changes further illustrate the limitations of human physiology in space. In microgravity, blood and other fluids shift toward the head, causing facial puffiness, congestion, and reduced leg volume. Over time, plasma volume decreases, the heart atrophies slightly, and blood vessels undergo structural changes. Astronauts returning to Earth often experience orthostatic intolerance, a condition in which standing upright causes dizziness or fainting due to insufficient blood flow. The cardiovascular system is adaptable, but these changes demonstrate that prolonged exposure to weightlessness stresses critical organ systems. The immune system is also affected. Studies show that spaceflight suppresses immune cell activity, increases inflammation, and may reactivate latent viruses such as Epstein-Barr and herpes. Combined with radiation exposure and nutritional challenges, immune suppression elevates the risk of infection, complicating long-term survival in space. Minor illnesses that are easily managed on Earth could become life-threatening in a spacecraft without immediate medical intervention. Neurological and sensory effects present additional constraints. Microgravity and radiation can alter brain structure and intracranial pressure, leading to spaceflight-associated neuroocular syndrome, SANS. This condition affects vision, causing blurred eyesight and changes in the optic nerve. Cognitive function may also be subtly impaired over long durations, with memory, attention, and motor coordination affected by the combination of microgravity, stress, and radiation exposure. For missions where rapid problem-solving and situational awareness are essential, even minor neurological impairment is a significant risk. Radiation exposure represents one of the most severe long-term threats. Outside Earth's magnetosphere, humans are exposed to galactic cosmic rays and solar particle events, which can damage DNA, induce cancer, and accelerate aging. While shielding and medical countermeasures reduce risk, no current technology can eliminate it entirely. Estimates for a mission to Mars suggest cumulative radiation doses that exceed safe thresholds established on Earth, highlighting the constraints imposed by space itself on human survival. Metabolic and nutritional challenges also define physiological limits. Microgravity alters protein turnover, calcium metabolism, and gastrointestinal function. Appetite suppression, altered taste perception, and nutrient degradation in stored foods increase the risk of malnutrition. Even small deficiencies in protein, vitamins, or minerals can amplify muscle and bone loss, impair immune response, and compromise cognitive performance. Nutrition, hydration, and metabolic monitoring are critical to preventing these cascading effects. Psychological stress interacts with physiological vulnerabilities. Isolation, confinement, and monotony can exacerbate sleep disruption, hormonal imbalances, and cardiovascular strain. Stress hormones such as cortisol influence bone density, immune function, and metabolism. Long-duration missions amplify these effects, demonstrating the inseparable link between mental and physical health in space. Historical missions provide insight into these limits. Valery Polyakov's 437-day stay aboard Mir represents the longest continuous human spaceflight. Despite rigorous exercise, medical monitoring, and controlled nutrition, he experienced bone loss, muscle atrophy, changes in vision, and psychological stress. Upon return to Earth, recovery was possible, but some physiological adaptations persisted for months. These findings illustrate that even under optimal conditions, there are inherent limits to human endurance in microgravity and space environments. Cumulative effects define the ultimate boundary of survival. For missions exceeding 1 year, multiple systems, musculoskeletal, cardiovascular, immune, neurological, and psychological, interact in complex ways. Compensatory mechanisms can delay the onset of critical failures, but prolonged exposure increases the risk of irreversible damage. Current research suggests that without advanced countermeasures, human survival beyond 2 to 3 years in space is highly uncertain. Technological solutions aim to extend these boundaries. Exercise devices, artificial gravity concepts, radiation shielding, optimized nutrition, and psychological support all mitigate physiological decline. However, even with the best interventions, natural biological limits persist. Individual variability also plays a role, as genetics, prior health status, and resilience influence how each astronaut adapts to the environment. Planning for interplanetary missions requires accounting for these variations to maximize crew survival. Understanding the physiological limits of humans in space is not solely an academic exercise. These insights guide mission design, habitat engineering, emergency protocols, and health monitoring strategies. They define the maximum feasible duration of missions, the necessary technological countermeasures, and the selection criteria for crew members. Every decision is informed by the delicate balance between human biology and the hostile environment of space. In conclusion, human survival in space is constrained by a complex interplay of physiological, environmental, and psychological factors. Microgravity, radiation, nutritional challenges, immune suppression, neurological changes, and stress collectively impose strict limits on endurance. While technological innovation can extend these limits, inherent biological boundaries remain. Understanding and addressing these risks is essential to ensuring the health and performance of astronauts during long-duration missions, defining the outer boundaries of human life beyond Earth. The next chapter will explore interplanetary travel and potential human colonization, focusing on the challenges, risks, and strategies for sustaining life on Mars, the Moon, and beyond. The prospect of traveling beyond Earth orbit and establishing human colonies on other celestial bodies represents one of the most ambitious goals of modern space exploration. While technology has advanced to sustain human life in low Earth orbit for extended periods, interplanetary travel introduces unprecedented challenges. The journey to planets such as Mars or permanent settlements on the Moon demands meticulous planning, robust life support systems, and comprehensive strategies to mitigate the physiological, psychological, and environmental risks inherent in space. The first challenge of interplanetary travel is duration. A round-trip mission to Mars, including transit and surface stay, could span 2 to 3 years. During this time, astronauts must survive in microgravity or partial gravity, endure continuous radiation exposure, and maintain psychological and social health. Unlike missions to low Earth orbit, resupply from Earth is impossible, requiring spacecraft to carry all necessary food, water, air, and equipment. The logistical complexities of transporting tons of supplies and ensuring system redundancy place strict constraints on spacecraft design, mass, and energy efficiency. Radiation exposure represents a critical threat during interplanetary missions. Outside Earth's protective magnetosphere, astronauts face continuous bombardment by galactic cosmic rays, GCRs, and solar particle events, SPEs. Prolonged exposure can lead to cancer, neurological damage, and accelerated aging. Advanced shielding is essential, but current materials provide limited protection against high-energy cosmic rays. Strategies under investigation include water-based shielding, hydrogen-rich polymers, storm shelters for solar events, and even magnetic or plasma fields to deflect charged particles. Managing radiation exposure remains one of the greatest barriers to long-duration human spaceflight. Microgravity during transit also imposes significant risks. Extended periods in weightlessness lead to muscle atrophy, bone loss, cardiovascular deconditioning, and alterations in fluid distribution. Countermeasures such as rigorous exercise, nutrition optimization, and artificial gravity systems, via rotating habitats or centrifuges, are critical to maintaining physical health. Partial gravity environments, such as the Moon, 16% of Earth gravity, or Mars, 38% of Earth gravity, mitigate some effects, but research is ongoing to determine the threshold of gravity necessary to sustain long-term musculoskeletal, cardiovascular, and neurological health. Psychological resilience is equally critical. Crew members on interplanetary missions face prolonged isolation, confinement, and communication delays with Earth. Unlike low Earth orbit missions, real-time support is impossible, and decision-making falls entirely on the crew. Strategies to mitigate stress include structured routines, recreational and social activities, virtual reality environments, and pre-mission psychological training. Monitoring mental health is essential, as even minor psychological disturbances can compromise team cohesion, operational efficiency, and safety in high-stakes environments. Life support and habitat design for interplanetary missions require self-sufficiency and closed-loop systems. Oxygen generation, water recycling, food production, waste management, and environmental control must function reliably over years. Current advances include hydroponic and aeroponic plant growth systems, microbial recycling, and regenerative life support technologies. Habitats must also balance operational efficiency with psychological needs, providing private space, communal areas, and Earth-like environmental cues such as lighting cycles and artificial landscapes. Nutrition and hydration are foundational to long-term survival. Interplanetary missions cannot rely on resupply, necessitating food that is shelf-stable, nutritionally complete, and diverse enough to maintain appetite and morale. Cultured meats, algae, and plant-based protein systems are under investigation for long-term sustainability. Water must be fully recycled, with redundancy and robust filtration to prevent contamination. Nutritional adequacy is critical to counteract microgravity-induced bone and muscle loss, immune suppression, and cognitive decline. Medical readiness is another essential component. In space, minor injuries or illnesses can escalate into life-threatening conditions. Interplanetary missions require onboard medical facilities, telemedicine capabilities, automated diagnostic tools, and potentially regenerative therapies. Preventive care, monitoring systems, and contingency planning are essential to maintain crew health when immediate evacuation is impossible. The Moon and Mars present additional environmental challenges. Lunar habitats must contend with extreme temperature fluctuations, abrasive dust, and a near-vacuum environment. Martian colonies face a thin carbon dioxide-dominated atmosphere, low gravity, cold temperatures, dust storms, and radiation exposure. Habitat design incorporates shielding, thermal regulation, pressurization, and energy generation. Local resources, such as regolith for radiation protection or in-situ water extraction, are critical for sustainability and reducing reliance on Earth-based resupply. Transportation and propulsion also define the feasibility of colonization. Conventional chemical rockets are energy-intensive and limit cargo capacity. Advanced propulsion technologies, such as nuclear thermal or electric propulsion, could reduce travel time and improve efficiency, mitigating some of the physiological risks associated with prolonged microgravity and radiation exposure. Faster transit also reduces mission costs and increases safety margins for crew health. Beyond survival, the long-term goal of colonization involves creating self-sustaining ecosystems. Closed-loop life support systems, renewable energy, local agriculture, and waste recycling are essential for permanent settlements. Developing these technologies on the Moon or Mars serves as a stepping stone for deep space exploration, providing insights into sustainability, resource management, and human adaptation in extraterrestrial environments. In conclusion, interplanetary travel and human colonization push the boundaries of human survival. The combination of radiation, microgravity, psychological stress, resource limitations, and environmental hazards defines strict limits on endurance. Technological innovations in life support, propulsion, habitat design, and sustainability are essential to extend these limits. Successful colonization requires integrating physiological, psychological, and environmental knowledge into comprehensive mission planning, ensuring that humans can survive, adapt, and thrive beyond Earth. The next chapter will examine extreme survival scenarios in space, exploring the limits of human endurance in emergency situations and unplanned exposure to the harsh environment of the cosmos. Space is an environment that allows no margin for error. Beyond the relative safety of controlled spacecraft, humans face extreme survival scenarios where the slightest malfunction, accident, or miscalculation can quickly become life-threatening. Understanding these scenarios is critical to preparing astronauts, engineers, and mission planners for the realities of long-duration spaceflight and interplanetary travel. One of the most immediate threats is sudden depressurization. A breach in the spacecraft hull or habitat exposes humans to the vacuum of space, causing rapid decompression. In seconds, air escapes, and body fluids begin to vaporize, a condition known as ebulism. Although human skin can withstand brief exposure, lung expansion and gas-filled cavities present severe risks. Historical experiments and simulations demonstrate that unconsciousness occurs within 10 to 15 seconds, and prolonged exposure beyond 1 to 2 minutes is fatal without immediate intervention. Emergency protocols include rapid sealing of compartments, pressure suits, and emergency air supply to prevent catastrophic outcomes. Life support system failures represent another extreme risk. Malfunctions in oxygen generation, carbon dioxide removal, water recycling, or thermal control can quickly compromise human survival. On the ISS, redundant systems and real-time monitoring mitigate these risks, but interplanetary missions magnify the consequences. With no immediate rescue, astronauts must rely on onboard repair capabilities, spare components, and contingency procedures. Failure to restore life support can result in hypoxia, hypercapnia, dehydration, or exposure to toxic gases, conditions that become critical within minutes to hours. Radiation emergencies pose both acute and long-term threats. Solar particle events, SPs, can deliver massive doses of ionizing radiation in a short period. Without protective shielding, astronauts can experience acute radiation syndrome, characterized by nausea, fatigue, immune suppression, and potentially death. Galactic cosmic rays, GCRs, contribute to cumulative exposure, increasing the risk of cancer and neurological damage over time. Emergency strategies include storm shelters within spacecraft, protective clothing, and rapid detection systems to alert crew to high radiation events. Even with precautions, extended exposure during interplanetary missions remains a formidable hazard. Extravehicular activity, EVA, incidents introduce additional survival challenges. Spacewalks are inherently dangerous, requiring complex suits, tethering systems, and precise coordination. Equipment malfunction, loss of tether, or suit punctures can result in rapid decompression, exposure to extreme temperatures, or uncontrolled drift into space. Astronauts train extensively in neutral buoyancy pools and simulations to manage these emergencies, but in deep space, EVA incidents could become fatal if immediate rescue or self-repair is impossible. Temperature extremes and thermal regulation failures also threaten survival. Space presents a paradoxical environment. Direct sunlight can heat exposed surfaces to over 120 degrees Celsius, while shaded areas drop below -150 degrees Celsius. Failure of thermal control systems can lead to hypothermia or heat stroke within minutes. Space suits provide limited protection, but in a vacuum or during habitat system failure, exposure to these extremes is often lethal. Micrometeoroid and debris impacts are another constant danger. Even tiny particles traveling at orbital velocities carry immense kinetic energy. Impacts can puncture spacecraft walls, damage life support systems, or compromise critical instruments. Protective shielding, redundant modules, and careful monitoring of orbital debris are essential for minimizing these risks. On interplanetary missions, meteoroid swarms around asteroids or comets present additional hazards that cannot be fully predicted or avoided. Medical emergencies in space represent one of the most complex survival challenges. A heart attack, stroke, or severe injury far from Earth poses unique difficulties. Limited medical equipment, microgravity complications, and delayed communication with medical experts restrict treatment options. Astronauts are trained in emergency medical procedures, and spacecraft include surgical kits and telemedicine capabilities, but some conditions may be untreatable in transit. Preventive measures, crew health monitoring, and comprehensive training are essential to mitigate these extreme scenarios. Psychological crises can also become life-threatening. Isolation, stress, and sensory deprivation can trigger panic, disorientation, or impaired judgment. In extreme cases, interpersonal conflict or mental health deterioration may compromise mission safety. Strategies to reduce these risks include regular communication with Earth, structured routines, virtual recreation, mindfulness training, and careful crew selection. Even with these measures, psychological resilience remains a critical factor in survival during emergencies. Combination scenarios amplify the danger. Imagine a solar storm occurring simultaneously with a life support malfunction during an EVA. Astronauts must contend with radiation, limited oxygen, temperature extremes, and isolation. These compound emergencies are difficult to simulate fully on Earth, but they highlight the need for robust contingency planning, redundancy, and adaptive problem-solving skills. Crew training emphasizes scenario-based simulations, teamwork, and resource management under pressure. Historical incidents provide valuable lessons. The Apollo 13 mission demonstrated the importance of improvisation and resourcefulness under extreme conditions. Following an oxygen tank explosion, astronauts survived by carefully rationing power, water, and oxygen, while mission control engineered solutions from limited resources. This event underscores that human ingenuity, planning, and resilience are as critical to survival as technology. In addition to acute emergencies, long-term survival risks such as chronic radiation exposure, microgravity-induced bone loss, and muscle atrophy can become extreme in interplanetary missions. These cumulative effects may limit mission duration or require partial artificial gravity, enhanced shielding, or regenerative medical interventions to sustain human life over years of travel. In conclusion, extreme survival scenarios in space demonstrate the fragility of human life in the cosmos. Sudden depressurization, life support failures, radiation events, EVA hazards, thermal extremes, debris impacts, medical crises, and psychological stress each pose immediate threats. Compound scenarios magnify risk, highlighting the need for redundancy, planning, and adaptive problem solving. Learning from past missions, integrating advanced technology, and training for emergencies are essential for preparing humans to survive in the unforgiving environment of space. The final chapter will synthesize all findings and explore the ultimate limits of human life beyond Earth, addressing how long humans can realistically survive in space and the future of interplanetary habitation. After exploring the physiological, psychological, technological, and environmental challenges of space, one question remains: how long can humans realistically survive beyond Earth? While advances in life support systems, habitat design, nutrition, and radiation shielding have extended the limits of human endurance, the space environment remains inherently hostile. Understanding these ultimate boundaries is essential for defining the feasibility of long-duration missions, interplanetary travel, and permanent colonization. The first constraint is microgravity-induced physiological decline. Muscle atrophy, bone demineralization, cardiovascular deconditioning, and fluid redistribution progress continuously in the absence of Earth's gravity. Even with rigorous exercise and nutritional interventions, complete mitigation is impossible. Data from long-duration ISS missions suggest that significant musculoskeletal deterioration occurs over 6 to 12 months, with partial recovery possible upon return to Earth. Beyond 1 to 2 years, the cumulative effects may surpass the body's adaptive capacity, particularly if combined with other stressors such as radiation or psychological strain. Radiation exposure represents the most critical long-term limitation. In low Earth orbit, the planet's magnetic field provides substantial protection, but interplanetary travel exposes humans to galactic cosmic rays and solar particle events with no natural shielding. Over time, radiation can cause DNA damage, cancer, neurological decline, and premature aging. Even with advanced shielding, acceptable exposure limits may be exceeded within 2 to 3 years on a Mars mission. The risk of irreversible damage imposes a hard ceiling on mission duration unless novel protection methods, such as artificial magnetic fields or enhanced biological resistance, are developed. Nutrition and hydration sustainability define another boundary. Long-term missions require food systems that maintain caloric balance, prevent deficiencies, and support physical and cognitive health. While hydroponic gardens, algae-based proteins, and regenerative life support systems provide partial solutions, uncertainties remain regarding shelf life, nutrient retention, and psychological acceptance. Extended missions exceeding 3 years will require highly reliable, self-sustaining food and water production, a challenge that current technology can only partially address. Psychological resilience further constrains human survival. Isolation, confinement, and communication delays increase stress, impair decision-making, and threaten team cohesion. Mental health support, structured routines, recreation, and virtual Earth-like environments can mitigate these risks, but prolonged missions carry unavoidable psychological strain. Historical data suggests that extreme isolation beyond 2 to 3 years significantly increases the risk of cognitive and emotional decline, highlighting the importance of careful crew selection and social support systems. Medical and biological limitations compound these challenges. Microgravity, radiation, and nutritional deficiencies create cumulative stress on organs and systems. Immune suppression, cardiovascular strain, bone fractures, and visual impairment may reach thresholds beyond which recovery is incomplete or impossible. While telemedicine, onboard diagnostics, and regenerative medicine offer partial solutions, the absence of immediate Earth-based medical intervention sets a strict boundary for human survival in space. The interplay of these factors defines the ultimate human survival envelope. Microgravity, radiation, resource constraints, psychological stress, and environmental hazards interact synergistically, reducing resilience and accelerating decline. Even with optimal countermeasures, current evidence suggests that humans cannot endure continuous exposure beyond approximately 2 to 3 years without severe physiological and psychological consequences. These limits may shift with future technology, artificial gravity, improved radiation shielding, or genetic adaptation, but for now, they set a realistic threshold for mission planning. Interplanetary colonization introduces additional constraints. While permanent settlements on the Moon or Mars are conceivable, they require self-sufficient ecosystems capable of producing air, water, food, and energy indefinitely. Closed-loop habitats, radiation protection, and psychological support must be sustained continuously. Even with advanced engineering, long-term colonists would face challenges associated with low gravity, radiation exposure, and resource management. The feasibility of multi-generational space settlements remains largely theoretical, as current technology and biological understanding impose strict survival limits. Despite these limitations, research and experimentation provide strategies to extend human endurance. Artificial gravity habitats, advanced shielding, regenerative medicine, optimized nutrition, and psychological support can push survival limits closer to multi-year durations. Simulations, animal models, and long-duration space station experiments continue to inform these strategies, offering incremental gains in human resilience. These innovations may eventually enable humans to survive for decades beyond Earth, though such scenarios remain speculative at present. Ethical and societal considerations also shape the boundaries of human life in space. Long-duration missions involve calculated risk, where astronauts knowingly face potential harm to advance exploration. Decision-making balances scientific gain, technological capability, and human welfare. Policies and planning must weigh the ethical implications of exposure to extreme hazards, ensuring that survival strategies prioritize health, safety, and informed consent. In conclusion, the ultimate limits of human life beyond Earth are determined by a complex interaction of physiological, psychological, environmental, and technological factors. Microgravity-induced degeneration, radiation exposure, resource constraints, mental health, and medical risks collectively define a survival envelope of roughly 2 to 3 years for current technology and human biology. While scientific innovation may extend this envelope in the future, these boundaries underscore the formidable challenges of interplanetary travel and colonization. Human survival in space is achievable, but only through meticulous preparation, robust technology, and an intimate understanding of the limits imposed by the cosmos itself. As humanity looks toward Mars, the Moon, and beyond, these insights serve as both a guide and a warning. Survival beyond Earth is possible, but life in space demands respect for its harsh realities, careful planning, and continual adaptation to the ultimate frontier. The exploration of space presents humanity with its most formidable challenges. From microgravity-induced physiological changes to radiation exposure, psychological stress, and resource constraints, every aspect of life beyond Earth tests the limits of human endurance. The 12 chapters of this documentary-style exploration have detailed the interconnected risks, technological solutions, and biological realities that define survival in space. Human adaptation to microgravity involves muscle atrophy, bone loss, and cardiovascular alterations, while psychological resilience is tested by isolation, confinement, and monotony. Nutrition, hydration, and life support systems are critical to sustaining health, and technological innovations, from air and water recycling to habitat design and radiation shielding, serve as lifelines in an environment hostile to life. Biological experiments and human models provide the scientific foundation for predicting risks and designing interventions, while extreme survival scenarios illustrate the thin margin between life and death in space. Ultimately, the research suggests that under current technological and biological constraints, humans can survive continuously beyond Earth for roughly 2 to 3 years. Beyond this threshold, cumulative effects from microgravity, radiation, and resource limitations impose severe risks. Interplanetary travel and colonization remain possible but require careful planning, advanced technology, and robust countermeasures to extend human life safely. The future of human space exploration depends on integrating physiological, psychological, and technological insights to maximize survival. As humanity prepares to venture to Mars, the Moon, and beyond, understanding the ultimate limits of human life in space is not merely academic, it is a question of survival, strategy, and the enduring drive to explore the unknown. This documentary-style narrative examines the limits of human survival beyond Earth, synthesizing research in physiology, psychology, technology, and space biology. It addresses the challenges of microgravity, radiation, nutrition, and mental health, as well as life support systems, habitat design, and interplanetary travel. Each chapter explores a critical dimension of space survival, from early biological experiments to extreme emergency scenarios, providing a comprehensive overview of the risks and solutions associated with long-duration missions. Key findings indicate that current technology and human biology allow continuous survival in space for roughly 2 to 3 years, highlighting both the possibilities and constraints of interplanetary exploration. The narrative concludes with a discussion of strategies for mitigating these risks, emphasizing innovation, preparation, and the resilience required for humans to thrive beyond Earth. This work serves as a detailed guide to the physiological, psychological, and technological factors that define human life in space, offering insight into the challenges of exploration, colonization, and the ultimate pursuit of survival in the cosmos.